So today we're going to talk about probability, and we're going to focus primarily on the definitional pieces and then some simple examples. Now, my hope is that this won't take the entire 2 hours and 45 minutes, so I can answer some questions, but if we end early, I'd rather end early today than try to overwhelm you with all of the content in 1 week. Today we're going to lay down the foundations so we understand what probabilities look like, how to work with them, and how to calculate relatively straightforward probabilities. Next week we'll learn a little bit more about how probabilities interact when we have multiple probabilities put together. Alright, so I will organize this discussion today in 3 parts. The first is just an introduction to the formal theory of probability. What does it mean to calculate a probability? What are we doing there? What kind of notation do we use? And then we'll talk about how to organize calculations that are related to probability. And finally, we'll focus a little bit on conditional probability. Conditional probability is particularly important, and it's not hard to be confused by it. And so I want to take time on that to really make sure it's clear. All right. So I think I've already answered this. I wanted to make a note to myself so I wouldn't forget. If I remembered, do let me know if you have any other questions that pop up. All right. So let's start talking about probability. In order to talk about probability, we kind of have to think about what kinds of things we're looking at. What kinds of things are we exploring when we calculate probability? So to do that, we need to talk first about what is called a random phenomenon. Okay, now this terminology is slightly different than the terminology in your book, but the ideas are exactly the same. Okay. A random phenomenon is a situation in which we know what outcomes can occur, but we don't know which particular outcome will happen. So we could list out all of the possibilities, but we're not certain which one's going to happen in a given situation. Okay. I'll use this example later in the discussion, but I'm a basketball fan, so if I consider who wins the NBA championship this year, well, there's a finite number of possibilities. I could list out all the teams in the league, right? I definitely know it's one of those things that's going to happen, but I don't know which one. So I could consider that to be a random phenomenon. Okay. Now, each time we observe a particular random phenomenon, that's called a trial. So another example, flipping a coin is the most common example used here. When I flip a coin, I may not know if it's going to land on heads or tails, right? But I know it's going to be one of those two things. And what I could do is I could flip that coin once, and maybe it lands on heads the first time. I could flip it a second time, and I don't know. Maybe it'll land on heads again, or maybe it'll land on tails. Each time I flip that coin, that is a trial. Okay? So in practice, we like to do this over and over and over again when possible, because we find some neat things happening when we do this over a long period of time. Okay. So the example I gave here is rolling a 6-sided die. That is a random phenomenon. Every time I roll the die, that is a trial. And the outcome is the number of pips that are showing when I roll the die. Okay. Now we typically use a number of different ways to represent probabilities, but we usually start with set notation. So bear with me, I'm going to show you just a few simple things about sets. But the sample space is one of the sets we particularly care about when calculating probability. When we talk about all of those outcomes that we know might be possible, the collection of all of them is what we call the sample space. And the notation we'll typically use for that is a capital S, again standing for sample space. And so if I'm considering again that same example, rolling a die, the possibilities are 1, 2, 3, 4, 5, and 6. Now what would happen if I were to roll 2 dice simultaneously? What would the sample space look like then?
Twice the same set again, twice.
So that's a good guess. It does kind of make sense that there'd be 6 possibilities for the first dice and 6 for the second. But if we take twice 6, what we're doing is we're adding those possibilities together. Will that account for all of them? It's a little hard to reason through this, and we'll see why in just a few minutes. But it turns out you actually want to multiply those possibilities. Okay. Here's the basic idea. Let's suppose I rolled them in succession. Okay, this is not typically how we do it, but if you did it that way, it might make it clearer what's happening. If I roll the first die, and I get a 1, how many possibilities are there for the second die?
There's going to be 6.
Yeah, 6, right? So for that 1 outcome on the first die, I have 6 outcomes on the second. Well, what if I rolled a 2 on the first die?
Still going to be 6.
Another 6, right? And those are going to be completely different as a combination because the first die is totally different. Same thing for 3, there's another 6, and for 4, there's another 6, and so on. So all told, there are going to be 6 6s that are possible. Okay? So 36 total possible outcomes. And usually the way we'll write that is with ordered pair notation when we have two things together. So I would write the ordered pair 1, 1 as rolling, well, snake eyes, as is often called, 1 and 1. I'd write 1 and 3 as a 1 on the first die and a 3 on the second. Okay. Now, interestingly, there are different ways to represent the same sample space depending upon the problem you're looking at. If I'm interested in the possibility of, well, I'm going into this. If I'm interested in the possibility of the sum of the two dice, then I actually don't necessarily have to have all of the information about which one is which. I simply need to know what their total amounts to. And so in that case, I could have any number between 2 and 12, and that would be sufficient as a sample space. But the nice thing about the first sample space... Go ahead. Okay.
Sorry, that was me yawning.
That's okay. We've all been there. It's a little early, and I haven't had enough coffee. I apologize for that. Hopefully I'll be coherent today. One of the advantages of the first sample space is each of those outcomes is what we call equally likely. Right? There's 36 possible outcomes, and I expect about 1/36 of the time to see each individual one, as long as the die are fair. Right? As long as the dice are fair. That's not true if I look at the sample space from 2 to 12. A 2 is far less likely than, say, a 6 as a sum. And the reason is because there's only one way to get a 2, and there's multiple ways to get a 6. Okay. And so it is kind of important to think about that. This is why we want to be able to outline what our sample space looks like. In some cases, there are multiple possible options, and each one has different advantages and disadvantages. Okay. So knowing specifically what your sample space is will help you a lot with understanding how to calculate these probabilities. So let's represent the sample space for two coin flips using, well, let's do set notation for now. Actually, yes, we'll do set notation. I will show you a tree diagram. I'm going to skip the Venn diagram for now. We'll see it later in this discussion. All right, so let's switch over to the document cam for a moment. So when I want to represent two coin flips, oh, great, two coin flips, I need to have a notation for the outcome of each coin flip, right? And so I'm going to use H to be heads and T to be tails. Okay? So what is the possible sample space for two coin flips? All right. What's the possible sample space? What could happen if I flip a coin twice?
We could have heads twice.
Okay.
You could have tails twice.
Okay.
You could have one head and one tail. One tail and one head, is that different?
Yeah, again, that's two different ways to represent it, depending on whether we care which one came first.
Okay.
What I would say is this is probably the better one to work with. It's what's called a finer sample space. it's more specific. So it can address more problems than the first one could. But if all I care about is a count of how many heads and how many tails, then I don't have to distinguish necessarily between these two. Right? But luckily, and we'll see this later, if I use this finer sample space, each of these is equally likely. There are 4 outcomes, and the probability of each is 1/4. So again, that will make my life a lot simpler. Okay. All right. So it occurs to me, my first day here, I forgot to write down the attendance. Let me do that really quickly. Oh, and one word of warning, I can't see the chat here, so if you have a comment you'd like to make, just unmute. That'd be great. I think that's everyone. All right. So this is the set notation version of the sample space. I could also use what's called a tree diagram. And when mathematicians talk about a tree, we really mean a graph that splits in specific ways. Okay? So when you're done and you draw the tree, it ends up looking a little bit like tree branches. And in fact, we use terminology that points to the same thing. So I'll start with a particular node representing the first coin flip. All right? You don't have to write this. I'm writing it here just so you know what it means. And on the first coin flip, I have 2 options. So I'm going to draw 2 branches emanating from that node. What are the 2 possibilities?
Heads or tails?
All right, so I'll put heads underneath this one and tails underneath this one. All right, now suppose I got heads on the first toss. Well, then what are the possibilities for the second toss?
Heads or tails?
All right, so again, I will split here in 2 directions with heads and tails. Okay. Well, what if I'd gotten tails on the first toss?
Next one could be heads or tails.
Could be heads or tails, right? And if it's a fair coin, each of these events is equally likely in every case, so a lot of things will be nice. We'll see how to calculate this using a tree diagram. But you can follow the tree diagram from the starting point to the ending point. And by the way, the end of a branch is suggestively called a leaf with when we talk about tree diagrams. Okay? So if I follow from the starting node here down to the leaf, I pass through H and H, so this is the outcome HH. Here I pass through H and then T. This is the outcome HT. And here I pass through T and H, and then T and T. So you can see that each of the 4 outcomes in my set is represented in the tree diagram. But the nice thing about tree diagrams is sometimes what happens on the first outcome here might influence the probabilities on the second outcome. And that's where it really helps to be organized in terms of a tree diagram. Okay? Maybe I'm rolling 2 dice, and I roll 1 dice first, and if it's an even number, I roll the second dice twice. And if it's an odd number, I roll the second dice once. Well, on the first, I'd have an even or an odd as possibilities, but then I'd have different outcomes for each of those branches. So the probabilities don't update in the same way. I have to make sure to organize it from which path did I start on, and then which path did I take next. And tree diagrams do that very well for us. Okay, we'll see this again in more practice later on. I'm thinking it's likely that it'll be next week when we talk specifically about how to use tree diagrams. They're very useful for Bayes' theorem, among other things. Okay. And we will see a Venn diagram later. Honestly, you know what? I'll show you what a Venn diagram in this situation might look like. Okay, I have two things I'm looking at. They're supposed to be the same size, but I'm a terrible artist. What can I say? You know what? No, I'm not going to do this with a coin flip. It'll be too confusing if I try to do it that way. To do it correctly mathematically, I have to be a little bit obtuse, so I'm not going to do that. All right. The key idea I want you to take away from what we've seen so far is when you're thinking about all the possible outcomes, there are multiple ways to represent that, but whatever you do to represent it, we call that collection the sample space. We will almost always use this capital S notation, so if you see that in probability, it means the entire sample space. All right. Now, some conceptual things to make sure you're aware of. There's this idea of the law of large numbers, which is actually really important to probability. And it's that if I were to take a random process and repeat it over and over and over again, in the long run, the proportion of times that a particular event happens is what we define to be the probability of the event. This is what's called an empirical probability. We'll see this in just a few minutes. So an example of that might be a coin flip, okay? What's the probability of heads and what's the probability of tails if I flip a quarter?
50-50.
And we usually think of it as 50-50, right? And that's when it's a fair coin. Are quarters fair? How would we know? We can flip a quarter like numerous times over and over again and just record how many times do we get heads, how many times do we get tails. Now let's say I do it once and I get heads. Does that mean the probability of heads is 100%? No, that's a very small number, right? Small sample size. I can't really conclude very much from that. If I flipped it 10 times and I got 7 heads and 3 tails, is this a biased coin? I mean, maybe, but that's definitely not enough evidence to say that it is. Right? So how do we do this? Well, we do it a lot of times. If I flipped it 1,000 times and I came up with 600 heads, well, now I think there's something to look at. This might be a biased coin. And by the way, I should tell you that this experiment has been done with a significant number. I forget exactly how many, but something on the order of like 10,000 coin flips. And it came out to about 50.2% or something like that heads. So it is actually slightly biased. Not by a lot, but it does look like there's actually a difference between the probability of heads and the probability of tails. Always keep that in mind. We can make a model where we assume that the coin is fair, but that's an assumption, and that may or may not hold true for a particular coin. All right. In order for this law of large numbers to work out, we do have to have 2 assumptions that hold true. First, every time, in this case, if I'm thinking of the coin, every time I flip the coin, the probability of heads or tails is the same for each attempt. Right? As long as it doesn't change over time, that's fine. And second, I want each of those events to be independent. That is, if I flip the coin and it turns up heads, I don't want the outcome of that event to have any impact on the outcome of the next coin flip. All right? Seems reasonable that both of those assumptions would hold true for a coin flip. But it is important to check this. There are situations where you might think about using the law of large numbers, but if you're careful, you'll notice that one or both of these assumptions are not valid. And in that case, the law of large numbers does not apply. Okay? If the outcome of one event can affect the outcome of another, then I could get a run of things that all are dependent upon whatever happened the first time. And that's not going to lead to a long-run probability calculation that is correct. Okay? All right. So this is just summarizing what I said with that specific example. If I have a fair coin, and I flip it a very large number of times, the number of heads out of the total number of coin flips should get closer and closer to a half. Okay? Again, it doesn't have to be exactly a half. It could be just a little above, just a little below. If I do this over and over again, and it truly is fair, then it should eventually settle near 1/2. Okay. You may or may not have heard of the law of averages, or regression to the mean, I guess is another way to think about it. This is a very dangerous assumption. It's kind of a misconstrual of the law of large numbers. It's actually very different. It brings in assumptions that are not necessarily true, and in fact in many cases are completely false. So here's an example. A gambler who's playing roulette. Let's see if we can read it here. A gambler who's playing roulette may notice that the wheel he's playing on has landed red the last 4 times. He's going to call black this time because he thinks black is due. Right, is that correct reasoning? We're going to assume that the casino's not cheating here or anything like that. If that's the case, then I would expect each spin of the wheel to be independent. And whatever the probability of red or black was on one spin is completely separate from the probability of red or black on a different spin. Right? And so in that case, no, this is not true. The probability of red and the probability of black should be the same as they were for each of the previous 4 spins. Okay? We don't have any guarantees it'll go one way or the other because it is quote-unquote due. Another example, suppose we have a center on a basketball team who's not a great free throw shooter, and she's hit 5 in a row. Will she hit the 6th one? Well, maybe, right? But chances are, in most cases, the probability of hitting the 6th one is pretty much the same as her free throw percentage in general, right? Unless there's some reason, like maybe she changed her shooting motion in the last since the last game, and that's why she's hitting these at this point. She's changed her shooting motion, and she's really gotten a lot better at shooting free throws. Perhaps that's possible. But in that case, the probability you're using is not the same as the probability that exists in this moment. So it is a violation of one of those 2 assumptions. All right, so that's the idea. Be careful, be wary of the law of averages, assuming that because you've seen some behavior before, you'll either see it continue or you'll see the opposite of it, because the opposite should be expected sometimes, right? It doesn't work that way if they are truly independent events. Then the probability each trial is exactly the same as it was on the previous trial, regardless of the outcome of the previous trial. So that's a really important distinction. Okay, so now we can talk about the 3 different kinds of probability, okay? We're going to focus on 2 of these in particular, but the first one is the one I've just described. It's called empirical probability. And when you think of empirical probability, what you're thinking about there is, if I were to test this over and over and over again, and record how many times a particular event occurred out of the total number of trials, that would be the empirical probability. Intuitively, it makes sense that this is a probability calculation. I'm simply saying, how often did it happen in the past? What was the likelihood in the past? And using that to project what I think the future probability will be. So that's one way to do this. Another way is a theoretical probability. I could make some simplifying assumptions and say, well, I think the probability of this piece is, well, if I think it's a fair coin, for instance, I might say I think the probability of heads is 1/2, and the probability of tails is 1/2. And then using that model, I can deduce the probability of, say, 3 heads out of 4 tosses. All right, we'll actually see how to do that in a unit or 2 from now. Okay. That is a theoretical probability. What we're doing there is we're building a model based on some simplifying assumptions. We might be assuming a probability based on we think it's equally likely that heads or tails will come out. Essentially, we're assuming it's a fair coin. Or there are other assumptions in other cases. When we do that and we build a model mathematically from it, that is called a theoretical probability. And then the last probability type is what we think of as subjective. And essentially what I mean there is it's a probability that represents your personal degree of belief. I believe the Lakers have a 25% chance of winning the championship this year. I may be deluded, but that's my personal belief, right? That's a subjective probability, okay? All right. Again, we're going to focus in this class on empirical and theoretical probabilities, because those are the 2 that are easiest to work with specifically. It's kind of hard to argue with this, even if it's not necessarily accurate. All right. So when we work with the sample space and we work with probabilities, we can assign probabilities to each individual outcome, but we need a few different things to work out. Okay? Every probability that we assign has to be a number between 0 and 1. I can't have a probability that's negative, and I can't have a probability that's greater than 1. Okay? Essentially, looking back at that empirical probability, I expect my probability to be a prediction for what percentage of the time, or what fraction of the time, I guess is a better way to say it, that I will see a particular event happen. And I can't have it happen a negative fraction of the time. I can't have it happen more than 100% of the time. It has to be somewhere between 0% and 100%. Right? I could write it as a fraction, I could write it as a decimal, whichever way I prefer to write that, but it has to be somewhere between 0% and 100%, and that's what this is saying. Okay. So for any particular event, any particular set or outcome or set of outcomes, the probability has to be between 0 and 1. When I put all of the possible outcomes together, and I find the probability of at least one of those outcomes happening, it has to add up to 1. Right? If I've listed out all of the possibilities and asked what's the probability something in that set happens, it has to be 1. It has to cover everything. Right? 100% of the time, something will happen in my list of possible outcomes. I may not know which one, but I know one of them will. And so the probability of the sample space is always exactly 1. We will use this idea of a complement. And so this is the notation I use with a C in the superscript. You may also see a prime symbol, like a single quotation mark. What that means is not that event. So for instance, if my event A is, well, I'm still stuck on this, the Lakers win the championship, then a complement is someone else wins the championship. Right? It's not the original event that I was talking about. Nicely, when I think about how P of S and P of A work together, I can find the probability of A complement by taking 1 and subtracting from it the probability of A. So if I think that the Lakers have a 25% chance of winning the NBA championship, then I think there's a 75% chance that they won't win the championship, that someone else will. So that's the idea. All right. Now, when we want to combine probabilities, there are a few key terms about events that will help us know how to do that. So the first of those is disjoint or mutually exclusive. It's two different ways of phrasing the same idea. If I consider two events to be disjoint, what I'm saying is it's impossible for both of them to happen together. They can't both happen. Maybe one can, maybe the other can, maybe neither can, but they cannot both happen together. Right? That's what it means to be disjoint or to be mutually exclusive. This mutually exclusive means that each one excludes the other as a possibility. So, for instance, the Lakers win the championship and the Nets win the championship. Those are mutually exclusive events. They can't both happen in the same year. One of them will, one of them won't. Maybe they both won't. But it's impossible for them both to win. Okay. That's mutually exclusive. Here's a nice feature of mutually exclusive events. If I want to find the probability that either event A or event B happens, and they're mutually exclusive, I can simply add those probabilities together. So to put numbers to it, let's go back to that same example I've been using as a theme here. I think the Lakers have a 25% chance of winning the championship. And I'm a homer, what can I say? I think the Nets have a 10% chance of winning the championship. What's the probability that one of those two teams wins? It'd be 25% plus 10%, which is 35%. And that's how it works. This is what it means to be mutually exclusive. If you want to find the probability that either event happens, you can simply add them together because they're mutually exclusive. They're completely separate probabilities. Okay. Now, what if we were looking in general? What if I want to know the probability that two events happen and I don't know that they're mutually exclusive? Well, in that case, I have to use what's called the inclusion-exclusion rule. Okay? Let me think about a way to explain this. So the probability of A or B happening, maybe I'll do it with an example. Suppose I think that the weather today affects whether there will be students in the classroom with me, right? That's not unreasonable. I could call event A the probability that it is, or excuse me, A is the event that it is raining today, and B is the event that there will be students in the classroom with me, say at least 2. Okay. Now those are separate ideas, right? But I could talk about the probability of one of those 2 things happening. Either it rains, or I have at least 2 students with me. Okay? Well, if I add those things together, let's actually switch over to the document cam again, if possible. If I add those things together, let's call A the event that it rains, and B the event that at least 2 students are in the classroom with me. Well, it's possible that it rains and I have 2 students with me. That's right here, right? It's possible that I have 2 students with me, but it's not raining. It's also possible that it rains and I don't have 2 students with me. In fact, it's also possible outside of this that not A and not B. Those are the possibilities, right? All 4 of those things. If I asked you for the probability of A or B, well, suppose I tried to do the same thing we did with mutual exclusion. I want to add those 2 probabilities together. I'm going to take the probability of A and add the probability of B, right? If you look at the regions that are involved in that, the probability of A is this left-hand circle. All right, so it's this part and this part. Both of those involve event A happening. Probability of B is this circle. So that's this part and this part. If I add those things together, I've covered everything, but I've actually double counted this middle part. All right, I counted it with A and again with B. So the way I can handle that is I can take away the overlap. Okay? If I do that, I've added 1, 2, 3, 4 together, and I took away the extra copy of the middle, and that means I have 1 copy of each of these. That's exactly what I want for the probability of A or B. Okay?
Okay.
So Venn diagrams help you organize that. They also are a great way to illustrate this idea. And I should warn you, for now we're doing this with just 2 sets. I can do this with 3 sets, with 4 sets, with 5 sets. And it's a lot more complicated thinking about how these pieces interact. But this idea is fundamentally the same. I can add up all of the different circles together. Then I subtract away the places they overlap. And depending upon the number of circles there might be some I have to then add back in because I got rid of them accidentally. And then that double counted some others, so I subtract away a smaller set and so on. And so you can keep adjusting this way. It is formally possible to figure out exactly what that looks like. It's much simpler with 2. And that's what we're sticking with for now. And I do want to show you what the set notation for that is. So OR In set notation, we usually use a union, right? Looks like a U, it's actually a little bigger than a U. And so I would call that the probability of A union B, when I'm thinking of these as sets. Still the probability of A plus the probability of B minus, well, for AND, in sets we call that the intersection. If you've seen that before, great. If you haven't, it looks almost the same, but it's upside down. These two statements say exactly the same thing. This is in words, and this is in set notation. Okay. You should be able to recognize both, hopefully. But as long as you've seen it here, you should be in good shape. Questions about the formulas here? It looked like someone was unmuting, but... All right. Again, this is called the inclusion-exclusion rule, if you've ever seen it before. We will talk about it again later when we do Venn diagrams in practice. All right. So now let's define conditional probability. So let's go to the next slide. Okay. So sometimes what happens between two events is completely separate, right? Knowing what happens with event A and event B, they have no impact on each other. Sometimes one event might influence the other. And if we want to be able to talk about when two events' probabilities might somehow interact or depend on one another, we have to bring in the notion of conditional probability. Okay? So it looks complicated, but if you say it in your head, it's actually not that bad. For two events A and B, the conditional probability of A given B, that's this notation, probability of A given B. It's the probability that A will happen given that we know B already has. Right? So if I assume B has happened, that might allow me to update the probability of A. Right? And what this is saying is, let's find the probability of A if we know that B happened. All right, so I do want to illustrate that. I'm going to talk through. Yeah, okay. I'm going to talk through this, and then perhaps show you another example on the document cam in a moment. So suppose you roll a 6-sided die. All right, the two events I'm going to consider. I'm a number theorist, so I can't resist doing this kind of thing, at least sometimes. But hopefully this makes clear how this might work. Let's suppose A is the event you roll an odd number. Okay? And B is the event you roll a prime number. What's the probability of A? Assuming this is a fair die.
%?
Yeah. We usually like to write probabilities as a fraction when possible. 50% or 0.5 or 1/2. Right? And the reason is because of the 6 possibilities, which are equally likely, 1, 3, and 5, that's 3 of them, are odd. 3 out of 6 reduces to 1 out of 2. So 1/2. All right. Maybe you remember this, maybe you don't, but if B is the event that you roll a prime number, what's the probability of B? Want to know which numbers between 1 and 6 are prime numbers? We've got a 1/6 chance with each one, so guess one. 1/6 chance with each one, so guess one. Any ideas? Well, let's go through them. Is 1 a prime number?
Yes.
Seems like it might be. It actually isn't. It's kind of weird. It's not a prime number. It's actually the identity for multiplication. So it's separate. How about 2?
Yes.
Yeah, 2 is a prime number. If I try to factor 2, the only way is just 2 times 1. So 2 is a prime number. That's one of them. Here you go, 1. How about 3?
No.
3 is a prime number. If I try to factor 3, it has to be 1 times 3. There's no other way to factor it. So that's another prime number. 4? That's not.
No.
5?
Yes.
Yeah, 5 is. The only way to factor it is as 1 times 5. And what about 6?
No.
No, you have to factor it as 2 times 3. Alright, so it looks like out of the 6, there's 3 of them that are prime numbers. So 3 out of 6, that's also a half. Right? It's not the same half, but it still is a 50% chance. Well, what's the probability of A given B? Alright, this is where it might help to switch over to the document cam. So the probability of A was the event that we had an odd. And we found that probability to be 1/2. Event B was the event we had a prime number. And that probability is 1/2. Now if I want to find the probability of A given B, well, what that means is I know it's one of these 3 numbers. I'm assuming that B happened. So I know it's a prime number. What's the probability it's also an odd number? I'll write this in words. I want to find the probability that I have an odd number given that it's a prime number. What do we think? If I know it was a prime number, it had to be one of these 3 possibilities. They're equally likely. So how many of those 3 possibilities are odd?
Two.
Yeah, 2 of them, 3 and 5. So the probability of A given B is 2/3. And I can check that because I can simply list out the possibilities in B. Since they're equally likely, I can count how many are also in A. And that'll be 2 out of the 3. Alright. So let's switch back to the slides again. So the probability of A given B is 2/3. In general, when we do conditional probability, we can actually use it to calculate what's called joint probability, the probability that both things happen. Okay? If I wanted to find the probability that the die toss was both a prime and odd, what I could do is I could take the probability that it is a prime, which is 1/2, and multiply that by the probability that it is odd, given it is a prime. That would be 1/2 times 2/3, or 1/3. And again, I can check that. The odd primes were just 3 and 5. That's 2 out of the 6 possibilities, which is, again, 1/3. Here's what it means conceptually. If I want to find the probability that A and B happen, what I can do is I can calculate the probability that A happens, and then multiply that by the probability that B happens, since A already did. Together, that means both A and B happen. Or I could organize it in the other direction. I could find the probability that B happens, and then assuming that B happened, find the probability that A will then also happen. Those things together assume that both A and B happen. This is how conditional probability works. This is called the general multiplication rule. It's very, very useful. And in fact, if you don't know a conditional probability, you can calculate it by just rearranging this equation. For instance, if I want to find the probability of B given A, I can take this equation and divide both sides by P of A. And then the formula will be P of B given A equals P of A and B over P of A. That's the first of those. I can do the same thing if I want to calculate P of B given A. Oh, excuse me, that's what I did here. I can do the same thing if I want to find P of A given B. I take this equation and divide both sides by P of B. The result is this equation. So this is the formula that we will use to define conditional probability. We're going to check all of these in just a moment with the example we just did by hand, just so we can see how they play out. Okay. All right. I guess I didn't formally define independent yet. When I say that two events are independent, let's do it over here on the document cam. I'll write it down. A and B are independent events if the conditional probability of A given B is the same as the unconditional probability of A given B. Right? That means knowing whether B happened or not doesn't change anything about the probability of A. That's what it means to be independent. Right? Similarly, if they're independent, the probability of B given A is the same as the probability of B without any conditions. Because, again, A and B are independent. They don't influence each other at all. So knowing that A happened doesn't help me with figuring out whether B does. Right? The probability of B is the same whether A happened or didn't happen. That's what it means to be independent. And one of the nice things is, because our two properties look, I'll show you just one of them, look like this. If the events are independent, then this equation becomes the probability that both happen is just the product of the probability that each one independently happens. Okay. And the reason is because if I take this equation and they're independent events, then the P of B given A is the same as P of B unconditionally. So that's why. And this is really the key idea that I want you to remember here. This gives us a way to test whether two events are independent, even if we don't know. We can find the probability that both happen. We can find the unconditional probability that each one happens. And we can check, is the product of these two probabilities equal to this probability? If so, they are independent. If not, they are not independent. Okay. So, before I go any further, let's say one other thing. Mutually exclusive or disjoint versus independent. Okay. Suppose A and B are mutually exclusive. What's the probability of both happening? Let's go back to the example of the basketball teams. Suppose A is the Lakers win the championship, and B is the Nets win the championship. Right? Those are mutually exclusive events. They can't both happen. So what's the probability that the Lakers and the Nets win the championship?
0.
0. That's always true if these two events are mutually exclusive. It's a key feature of being mutually exclusive. It's actually what it means definitionally. Can they be independent then? So here's a question. Is P of A intersect B equal to P of A times P of B? That's the independence question. Or
No.
Right, it's not. It's not the case. With the numbers I gave you before, the Lakers have a 25% chance. The Nets have a 10% chance. This product would be a 2.5% chance. So there's a 2.5% chance that they both win. No, that's completely off the wall. That's not possible. Okay?
115.
So by this definition, not independent.
Tuesday.
Another way to see it is by that more direct definition. Probably A given B. Sorry about that.
Yeah, it's not the one I'm looking forward to, but they
Right.
tell me I'm going blind, so we got to
Probability
do
of A,
something.
with the numbers I gave, was 0.25. Probability of A given B. What's the probability the Lakers win the championship given that the Nets won? Zero. If the Nets won, then the Lakers can't also win. It's just not possible. Okay, so that's another way to see it. Probability of A given B, and probability of B given A are both equal to 0. Okay. That's what it means to be mutually exclusive. It means the conditional probabilities in either direction are 0, and the joint probability is 0. They can't both happen, and if one of them does, the other cannot. That's what mutually exclusive means. Independent, on the other hand, means that knowing whether one happened or the other, or did not happen, has no influence on the probability of the other event happening. All right? So knowing whether B happened or didn't has no influence on A. This is not the case with the Lakers versus the Nets winning the championship. This probably is the case, at least I hope, for whether it rains today and whether the Lakers win the championship. All right? The probability of the Lakers winning the championship, given that it rained, I hope it's exactly the same as the probability of the Lakers win the championship without knowing about rain or not. Okay? I would assume there's no influence from the rain on whether they win. But I don't know, maybe LeBron slips on the way into the Crypto.com arena at this point. And in that case, yeah, it would have an influence. But outside of that, I don't see any way that the rain will influence their chances of winning. All right, good. Any questions about the basic definitions, mutually exclusive and independent at this point?
Yeah, does this mean we can figure out if the Bengals are going to beat the Rams in the Super Bowl?
If we make enough simplifying assumptions, yes, but the danger lies in those. So, unfortunately, I'm not sure I would rely too much on the calculations we get.
All right.
Good thinking, good thinking. All right, and on that note, let's take our first 5-minute break. By my clock, it's 10:05. We'll return at 10:10. I'll see you in a few.